All right, let's get into this section. So the question was about in 14.3, the last example. So I'll scroll down to that. Where is it? Here it is. Last example. Verify that the function is a solution to the three-dimensional Laplace equation. I've done this as a short video, so you can find that as a follow-up video. I'll just show you where it is. So under the lecture notes, you can see right here under the 14.3 section, there's the partial derivatives, and then I've got last example. So you can have a look at that and see that last example done. And it's also filled in on the filled in version of the notes as well. It was an example of partial differentiation. So you just do your 3 second order derivatives using symmetry to get the other 2, and then just see that they verify the equation. So Eduardo, you posted a, nope, there's no timeline on regrades. You know, in short, so Eduardo's question's about, is there a timeline for the horizon for which you can request a regrade on an assignment? And you may have been informed it was a week. That's not true. I mean, it's generally a good idea to get any concerns in within a week. But we of course had the midterm to occupy some of our minds. So, you know, generally there's no horizon on regrades for assignment. If you catch the mistake, you just bring it to my attention. Yeah, just bring it to my attention.
Okay, thanks for letting me know.
Yeah. All right, let's get into today's topic. Today's topic is tangent planes and linear approximations for multivariable functions. I'm going to go back to our construction that we had for partial derivatives. So the idea was, I'll turn a few of these things off. The idea was we have a surface and a point on that surface. And what we'd like to do is construct a plane through that point on the surface that best approximates the surface there. This is the analog to the tangent line, but now for surfaces. So the idea, if I zoom in on this, that plane should be a pretty good approximation, sort of sneaking it in at the top of the screen there, but it's doing a pretty good job of, at least nearby this point, of approximating the points on the surface. If I move far away, then the plane is probably not going to be a good approximation of the points around this point in question, but at least close by, points on the plane are roughly close to points on the surface. Same notion of a tangent line, but now we're looking at a tangent plane. The way we construct this is essentially through this idea of going in the x direction, constructing the tangent vector that points in the x direction. We'll see that's related to the x partial derivative. Doing the same thing in the y direction, we'll see that this tangent vector is related to the y partial derivative. Taking the cross product of these two, because those are both vectors living in the tangent plane, that gives us the normal vector to the plane. And with that normal vector to the plane and the point that we're interested, the plane going through, that's enough to construct the plane itself. We'll see that this normal vector, we don't technically have to take the cross product of these two vectors, because we're going to see that the normal vector has a very nice representation that we can jump straight to. So let's do that. So here's our situation. Here's our setup. We've got our plane. I'm going to draw the plane. I won't draw the surface in the background because we'll just focus on a plane right now. So we've got a plane. It's passing through a point P. That's x naught, y naught, z naught. And we're interested in finding a condition on any other point that lives in the plane. We'll call it point Q with components x, y, and z. And so now with this other point, what are the conditions? Well, we have a normal vector to the plane. that will assume will be given as well. So that's A, B, and C. And that normal vector has to be perpendicular to any vector that's parallel to the plane. So any vector from the point you know on the plane to the point in question that you're trying to decide if it's on the plane or not. So these have to be perpendicular to each other. And so what we have is that this construction or this visualization is what we need in order to write down the equation of the plane. The dot product of the normal vector and that blue vector has to be equal to 0. And that's what this equation is telling us. So now from this equation, what we can do is so plane can be written in the form. So we'll solve for z. So we're going to go z minus z naught is equal to, and we'll get, I'm going to write it as a little a times x minus x naught plus a little b times y minus y naught. So what I've done is I've moved the c z minus z naught. Well, maybe I'll think about it this way. I've taken all of this stuff, moved it to the other side of the equation, and then also taken the c in front of the z minus z naught and moved it to the other side. So when I've done this, what I get is an equation that looks like this, where a is equal to, little a is equal to negative big A over c, and little b is equal to negative big B over c. So I've just cleaned it up a little bit and written the plane in this form. The reason I've done this, the reason I've written the plane in this form, is to try to draw an analogy with calculus 1 and tangent lines. So when we write a tangent line to a function at a particular point, we can write it as y minus y naught is equal to the derivative times x minus x naught. And that's kind of what the form is I'm looking at here. It's just I've got a, little a and little b. And the main idea is that little a and that little b in this equation, they're actually going to be the partial derivatives. They're going to be the x partial and the y partial. So that's what we're going to see. So we will see, put this in a different color. We'll see that a is equal to the x partial derivative and b is equal to the y partial derivative. So that's where the partial derivatives are going to come into play. So it's a very nice analog to a tangent line. To get a tangent plane, you just do the same thing you would to get a tangent line, except you got two variables now. And so for each of the variables, you take the derivative and you form the equation of the plane in this way. So this will be the form of the equation that we will typically work with the most when we are dealing with tangent planes. Okay. So that brings us to our definition of the tangent plane. Suppose that f has continuous partial derivatives. An equation of the tangent plane to the surface, z equals f of x, y, is z minus z naught is equal to the x partial times x minus x naught plus the y partial times y minus y naught. So I still have to justify this. I still have to show you that the little a and the little b from the equation above are actually the partial derivatives. But that's what this, essentially this theorem is telling us. So let's go ahead and see why that's the case. Okay, so we're going to prove this now. And the way we're going to prove it is by our construction that we have done with those curves in the x and y directions. So what are our tangent vectors? So I'm going to go back to our construction here. What I'm going to work out is what these tangent vectors are. This green vector and this red vector. What are the green vectors and the red vectors in this diagram? So the tangent vectors, let's just say maybe I'll write it like this. So the curve in the R1 well, maybe I'll say x direction, the curve in the x direction on this one here. So I'll show you in the diagram. So that's this curve here, this black curve. We're going to find that green vector. So we're going for the curve in the x direction. I'll call it r sub 1 of, let's call it x. So that means the x variable is changing. The y variable is not, because we're going in the x direction. Our y values are remaining constant, so that's a b. And then we've got the f of x comma b. So that's our curve in the x direction. That's that curve that's living on the plane, but just allowing it to change in the x direction. And so then the tangent vector at, let's say AB again. Actually, I don't want to use AB in this case. I'm going to change this because I've used little a and little b above. So I'm going to say the point we're at is not AB. The point we're at is x naught, y naught. So curve in the x direction through x naught, y naught. That's what we're going to look at here, through x naught, y naught. And therefore the tangent vector at that point corresponding to x naught, y naught, let's call it capital T1, for T for tangent. That's going to be given by the derivative of this at the point x naught. And so when I differentiate my R1 vector, vector valued function, with respect to the only variable it has, and that's x, I get the first derivative is 1, the second derivative is a constant, and the third derivative is our partial derivative with respect to x, evaluated at x naught, y naught. So that's our tangent vector in the x direction to our surface. And we can do the same thing. So that was essentially step 1. Step 2, we could do curve in the y direction through the point x naught, y naught. And that's given by, let's say, R2y, which is x naught, y, f of x naught and y. So that's our curve that's living on the surface that's in the y direction. So I'll flip back here to our construction and I'll do actually I'll get the y direction one. There we go. So what we're doing here is we're cutting it with a plane. Oh, sorry, that's the x direction. I've got to get there's the y direction. So we're cutting it with a plane of some particular y value. We've got our curve that we're just constructed now. The x value is allowed to change along this curve. Oh, my apologies. I'm doing the second one here. I got to get these right. So now we are going in the y direction. I think I might have labeled these ones wrong here. Nope, there we go. Looks good. So in the y direction, got it now. So this is a fixed x value, x naught. The plane x equals x naught, cutting our surface. We are getting that black curve of intersection. That black curve of intersection in our diagram is given by the equation we just wrote down, R2. And then we construct the derivative of that vector valued function, and that gives us this red tangent vector. So that's what we've done for our construction. We've constructed this red tangent vector by taking this derivative. So let's do that now. Tangent vector at x naught, y naught. That gives us T2 is equal to the derivative. I see that I've missed the prime up here. So notice there's a prime missing there. We had to take its derivative. So that's now down here, our 2 prime of y is equal to 0, 1, and then the y derivative, x naught, y naught. So now we've got these 2 tangent vectors to the surface. They're 2 vectors that are tangent to the surface, but they're pointing in different directions. Now, if I want to find the normal to the surface at x naught, y naught, what we do is we take the cross product of these 2 tangent vectors. And so that's going to be I hat, j hat, k hat, 1, 0, f sub x, x naught, y naught, and 0, 1, f sub y, x naught, y naught. That's our cross product we want to take. So we'll go ahead and take our cross product. So for the first component, we are going to cover up, I'll put this in a different color because I'll cover them up temporarily. We're going to cover up that one and take the cross ratio here. So that would be 0 times f sub y minus 1 times f sub x. So that's going to be a minus f sub x, x naught, y naught. And then we're going to do the next one. And that's going to be the 1 times f sub y minus the 0 times f sub x with an extra negative sign in front because it's the second component. So that's a negative f sub y. And I'll just move this over a bit so I can fill in the rest. X naught, y naught. And then lastly, the third component is just going to be a 1. So that's our normal vector. We can use this normal vector, or we can use the negative of it. Either one works, but we'll use this one because what this tells us is that now the tangent plane is given by the normal vector, so the x component of our normal vector, negative f sub x, times x minus x naught, plus the y component of our normal vector, times y minus y naught, plus the z component of our normal vector, times z minus z naught. That's equal to 0. And rearranging, we can write it as z minus z naught is equal to f sub x, x minus x naught, y naught, sorry, f sub x, x naught, y naught, times x minus x naught, plus f sub y, x naught, y naught, y minus y naught. And so there's the equation of our tangent plane. And we've just figured out that those 2 values that are sitting in front of the x naught, x minus x naught, and y minus y naught, those little a and little b's from way above, those should be the partial derivatives. The other thing we get from this is, as I've said, the normal to the surface. Right, I said normal, we construct these 2 vectors from that diagram, take their cross product to get the normal, but the normal actually has a nice form that we don't have to recompute every time. This was our normal vector. It was the vector made up of the x partial, the y partial, and 1. And we can either put the negatives on the x and y partial, or we can negate this whole vector, just have the vector that points in the opposite direction, and that would be f sub x, f sub y, and negative 1. Either one can be used as a normal vector, but it means that there's a nice way to just compute that normal vector. All right, so that gives us our expression for the tangent plane, which means it just depends on the x and y partial derivatives. Yep, so the question was, y is in curve 1. So this curve here, y is y a constant. Why did I call it y naught? And so that comes back to this construction here. I'll turn everything off. And so what we're interested in is I want to know what's going on at this point on the surface. So, and I'm going to use the fact that we have space curves and we know how to deal with space curves, curves in space that we can then find tangent vectors to those curves from by taking their derivatives. So with this one, what we do is we cut it by a plane. So I'll go down and I'll just turn a couple of things off. So we've got our plane. I'll turn off the vector and I'll turn off the plane in a second. So the idea is I take this plane that passes through that point. And since this plane is parallel to the XZ plane, it means this plane is defined by y is equal to a constant value, namely the y value of the point we're at. So now I'm going to turn off that plane because what that did was that gave me this curve. How did I get that curve? Well, the only thing that's allowed to change, if I stare on it this way, this curve consists of all points where the y value is a constant, namely the y value of the point that it's passing through. So this curve consists of x values are allowed to change, the y value is constant, and the z value depends on the x and y value. It's f of the x value you're at and the y value you're at. And so when I flip back to the slide, that's precisely what we wrote down here. We wrote down the curve where the x value is allowed to change. That's why I made it a function of x. The y value is a constant, the y value of the point that we're passing through. And the z value depends on the x and y values so that it actually lives on the curve. That's why we're using the z component as f of x, y naught. So it actually lives on the curve itself. And that's how we got that one. And similarly for the next one, we just took the x value to be constant and the y value to change. That gives us our two directions. So we got these two directions, one direction, another direction, and then we took the tangent vectors in those two directions to get two vectors that are parallel to the tangent plane, and then took their cross product to get the normal. Yeah, no worries. All right, let's go ahead and find the equation of the tangent plane to the surface. I'll leave the equation of the plane just in view up above. So we want the tangent plane to the surface. Z is equal to the square root of 4 minus x squared minus 2y squared at the point 1, -1, 1. So the first thing we want to do is, maybe I'll just call this something. I'll call this f of x, y. So we want to write down what the x derivative is. So the x partial. And so that would be 1 over 2 times the square root of 4 minus x squared minus 2y squared. So that's the derivative of the outside function, the square root function, times the derivative of the inside function, -2x. And so this becomes a -x over the square root of 4 minus x squared minus 2y squared. So that's our x partial. We can go ahead and find the y partial. It's almost the same, except for a slight little change because of the value in front of the y squared. So it's the derivative of the outside times the derivative of the inside. In this case, that's a -4y. So that becomes a -2y over the square root of 4 minus x squared minus 2y squared. Okay, so we've got those partial derivatives. Now we're interested at the particular point in question. So we'd like to know what is the x partial at 1, -1. And so we plug our 1 and our -1 in. So that becomes a -1 square root of 4 minus 1 minus 2. Or in other words, -1 over √1, or just -1. And then we can get our y partial as well at 1, -1. So that if we look, well, I'll just do it. It's -2 times -1 all over the square root. The denominator is just the same as it was in the previous one. So this becomes a 2. So those are our values. for our partial derivatives. And then we can get our tangent plane now by taking z minus the z coordinate of the point we're at is equal to, so I'm using the formula at the very top of the page, the x derivative, or the x partial, times x minus the x coordinate of the point we're at, plus the y partial, times y minus the y coordinate of the point we're at. And so there's our tangent plane. We can clean it up a little bit. Z minus 1 is equal to negative x plus 1 plus 2y minus 4. And so that I can bring the x to the other side. That becomes an x minus a 2y plus a z. And then I could put all the constants on the other side. So that becomes a 2 minus 4, or negative 2. I think I've got a negative 2 here. That looks fine. Did I? Oh, that's the mistake. I'm wondering, why did I? It doesn't look like I got the answer that I got before. And some of you probably noticed it. Exactly. Isn't the y coordinate negative 1 rather than 2? Yeah, exactly. So this, I don't know why I wrote down a 2 there. That should be a negative 1. Thank you. And then that means that that's a 2 times a 1, which leaves me with a 2 here. And so that gives me a 4 overall on this side. Okay. So of course, the way you'd want to make sure we didn't make mistakes in our calculations is once we get to this, we're like, it's the tangent plane. Okay. So if that's the tangent plane, then what's sitting in front of the x, y, and z should be, so what's sitting in front of the x should be negative f sub x, and it is. What's sitting in front of y should be negative f sub y, which it is. What's sitting in front of the z should be 1. And we would check that 1, negative 1, 1 is on the plane. So we just substituted in 1, negative 1, 1. So that becomes a 1 plus a 2 plus a 1 is a 4. And so good. It is a point on the plane. So we can do those quick double checks to make sure we didn't make any calculational errors. All right. So that's tangent planes. The rest of this section is really about what can we do with tangent planes, so linear approximation. What else can we do with tangent planes? Well, we can ask the question of when does one exist or not. That's a question of differentiability. And the last thing we can do is talk about differentials. So as our inputs change a little bit, as our x's and y values change a little bit, how does our function value change? Does it increase? Does it decrease? So those are the last 3 topics, but they're all deeply rooted in this idea of the tangent plane. So linearization. If we're staring at a function, z equals f of x, y, and it has continuous partial derivatives at the point a, b, then the linear function whose graph is given by the tangent plane is called the linearization. So if we look closely at this, this is really just this value here. Maybe I'll put it in a different color. This value there is really just our z naught value. That was the corresponding z coordinate of the point on the surface. So this linearization is, I'm just going to scroll up a little bit. It's really just taking our tangent plane and taking this z naught value and just moving it to the other side of the equality and getting an expression z is equal to z naught plus the derivative times x minus x naught plus the y derivative times y minus y naught. So all this linearization is just move the constant over, get your expression for z, that's the tangent plane, and then just turn it into a function and just call it L of x, y. So our tangent.
Sorry, can you?
Yep.
Can you repeat that again? Didn't understand that.
Sure, we've got a equation for a plane that looks like this: f sub x, x naught, y naught, x minus x naught, plus f sub y, x naught, y naught, y minus y naught. So that's our equation of our tangent plane, just been reorganized a little bit. And now I want to turn this into a function. So there's my z value. So I want to turn this into a function so that when I plug an x value in and a y value into it, then what comes out is the z value. So this is almost a function, except I've got this minus z naught. So what I'll do is I'll take it and I'll just move it to the other side of the equality as a z naught. And now that's a function. So now this is a function. And this function gives us the z value on the tangent plane, given any x and y value that you're interested in. And so that's what we're going to call L of xy. It's a function of xy. So all we did was push the z naught to the other side and make a function out of it. And what this linear function is essentially the function that defines the plane. So now we can, if I go back to our construction, basically what we've done is we've just created a function now. I'll turn a few of these things on and then get rid of them so that we can focus on the tangent plane. So what we've done is we've got this function giving the surface, and we created a new function that gives the plane now. This is the way I get this plane is z is equal to the z coordinate of the point we're at plus the x derivative times x minus x naught plus the y derivative times y minus y naught. That's how I create that tangent plane. And now we can say, what is the value of the point on our surface, the z value of a point on our surface for some xy value that are pretty close to this one. So I move a little bit away. What's my z value going to be? Well, since my tangent plane is a close approximation to the surface, I can use the tangent plane to get values on my surface, or at least approximate values on my surface. And so that's what this next line is saying. Saying now you've got in some sense, the most straightforward kind of function there is to deal with. That is a linear function. The linear because the only places the variables appear are here, x and y. If you want to think of it by analogy, if I look back at the expression we've computed above, and I'll write this in that form of a linear approximation, it's going to be z is equal to 4 minus x plus 2y. This is the equation of the tangent plane, but now we've written it as a function, and this is what we're calling L of xy. It's just a linear equation, and so it gives us the equation of a plane. And I can use that to approximate my function. Yep, you got it. The plane is that best flat approximation. It's not the best approximation in general, because if you think about calculus 1, we had linear approximation, but then we bumped it up when we got into calculus 2 and did things like Taylor approximations. So approximating it with a quadratic, approximating it with a cubic, approximating it with a quartic. And then ultimately we went the full gamut and just said a Taylor series. But those were approximations through polynomials. We get the same idea here, but we're just starting with this is the best way to approximate the surface with a flat object, a plane. We could try to approximate it with a quadric surface as well, some degree 2 polynomial, or we could go for a degree 3 polynomial, etc. So we're at the tip of the iceberg here, but we're just going to focus on the linear approximations. So yeah, that's a good observation. What we're talking about here is just approximating the surface in the best way possible with a plane, and that's the tangent plane. And so that gives us our linear approximation formula, which says the values on the function, if we're trying to find their approximate values, we can use a tangent plane to approximate them. And that means we are using a function of this form to approximate values on our surface. So let's go ahead and do an example with this. Find the linear approximation to z at the point 1, 2. Okay, to get our linear approximation, we're going to need to know our derivatives. So we'll go dz dx, get our x partial, that's 6x minus 9y. And we're really interested at the point 1, 2. So let's go ahead and compute the value there. So I'm going to switch, I'm using the Leibniz notation now just to get a contrast from that subscript notation. So this is going to be x equals 1, y is equal to 2. So the value of our derivative at that point is going to be 6 minus 18, or negative 12. Then we'll also need the derivative in the y direction. That's going to be 6. Oh, my apologies, there was a square there. There's a square. That's a cube, so it's a square. So there would be a 6 times 1 squared, which is still 6. So the answer is still negative 12. I just missed the square in the derivative. Similarly, over here, we get a 6 times y squared minus, and the derivative with respect to y is a 9 times x. Then we'll work out the derivative at the point in question. And this becomes 6 times 4 minus 9, or 24 minus 9, which is, in this case, 15. And so now we can write down our linear approximation, or our linearization. So this is L of xy is equal to, and it's the function value at 1, 2 plus the derivative at the point in question times x minus the x coordinate of the point we're at plus the derivative in the y direction times y minus the y coordinate to the point we're at. And so we can just put all of this stuff together. What's f at 1, 2? So I plug 1 and 2 into our expression for our function, and I get 2 times 1 cubed, so that's 2 plus 2 times 2 cubed, so that's 2 times 8, that's 16. So I get a 1 plus, sorry, I get a 2 plus a 16 minus a 9 times 2 minus an 18. And so that's our function value, which ends up being 0, plus negative 12 times x minus 1 plus 15 times y minus 2. So in other words, it's negative 12 x minus 1 plus 15 times y minus 2. Or we could simplify this a little bit and write it as negative 12x plus 15y is equal to, or not is equal to, but the last term is the constant, so that would be negative 30 plus 12, so that would be negative 18. So I'm going to leave it like this, the line before, just because I don't need to simplify it down if I don't have to. This one I kind of like a little bit better because ultimately I'm going to maybe be interested in knowing what happens as I take my x and y value a little bit away from 1 and 2, and leaving it in terms of these differences might be nicer, might be easier to work with, but we'll see. So there's our linear approximation. And we want to approximate the y coordinate of the point that belongs to, so this is a separate question, but it's related to the work we've done. So let's approximate the y coordinate of the point that belongs to this curve here. So maybe the first question to ask is, this is a plane curve now. So because it's referring to it as a curve, it means we're not thinking of that as a surface in 3 dimensions. It belongs to this curve. So this is something that lives in the xy plane. What's the z value for the points on this curve? So if I pick a point x, y, and I'm thinking of it in maybe in space, z. Well, the z value for points on this curve, yeah, it's 0. So you can see the 0 sitting right there, and that 0's indicating that we're taking z to be 0 to get this curve. We're looking at how this surface intersects the xy plane, so we're looking at z equals 0. So that means we are interested in when z is equal to 0, x is equal to 1.1, 1.1 because that's the value right there. So I'll maybe draw an arrow. The y value is approximately, well, what is it? We've got our surface is best approximated by this plane. And so that curve is going to be best approximated by this plane where it intersects the xy plane. So when z is equal to 0. So that means the y value is approximately given by the solution to this. When the linearization, the L of xy, when it has a z value of 0, that's -12, 1.1 minus 1 plus 15 times y minus 2. So I took the linearization and I said that's a good approximation of our surface. And so it's a good approximation of how our surface intersects the xy plane. So I'm going to look at how this linearization intersects the xy plane, because that's going to give me an approximate value for y. And so now we can go ahead and we can solve this equation. 0 is equal to -12, 1.1 minus 1, so that's a tenth. So that'd be -12 over 10 plus 15 times y minus 2. And so we can just solve that using algebra, and we get something like 52/25 for our y value. So that's our approximation for our y value. Just solve this linear equation. Right, so again, the idea was we have a surface, we can construct a tangent plane to that surface, and then any question about what's going on around the point we constructed our tangent plane at, in this case, around the point would have been around the point 1, 2. We can use our linearization, our tangent plane, to answer questions about what the surface is doing around that point. And you can see that this y value is roughly 2 plus 2 over 25. So it's a value that's very close to 2. And we expected it to be very close to 2, because when values are very close to 1, the y value should be very close to 2, because we're taking the tangent plane at the point 1, 2. Yeah, we didn't need to use the whole f of x y equals z naught. Oh, maybe I'll phrase it this way. There's the one place that we use the fact, and that was right here for the point in question. X naught was 1, y naught was 2, and z naught is given by f of 1, 2, and we computed that. That turned out to be 0. So that's our z naught value. That came up in this equation of the tangent plane. Once we have the tangent plane, we can use that to approximate the surface at that point. All right. Then that leads us into what we're going to call the increment. So if I have a function f, which gives me z values for inputs x and y, and when I change my input a, or my input x, from a value a to a value a little bit away, and I also change my value y from the value b to something a little bit away, then the increment is how the function value changes. So it's the function value at the point you've moved to minus the function value of the point you were just at. So the idea is we're at a point and I'll use it in terms of our, that's not x, this is x on this axis. So we've got x and y, and I move a little bit away to an x plus delta x, and I move a little bit away to a y plus delta y. And I want to know up on my surface, there's the 2 points in question. So this first one is my z value that I'm starting at. And then the next value is what I get when I move a little bit away. So this is going to be our z plus delta z. And that was the increment, the change that had to get made to our function in order to account for the changes in the x and the y values. So I move a little bit. The idea here is I move a little bit in the input. How much did I have to move up or down in my output? And that's known as the increment. And the idea with that is our linear approximations give us ways to figure out approximately how much this has changed. This is going to be approximated by what we call the differential. And we'll see that and probably get to that at the beginning of next class. But for right now, we'll just wrap it up with this definition of differentiability. So the definition of differentiability is that a function is differentiable at a point if this increment can be expressed in the form of basically the change in the x direction plus how much you've changed your x input by, plus the rate of change in the y direction by how much you've changed your y value by, the product of those, plus some small changes. What this really means is that a function is differentiable if you can approximate it by a plane. And I'll finish with a picture. Here's our picture. The bottom line is a function is differentiable at a point if you can approximate it by a plane. If I look at this one here, no matter how far I zoom in and zoom in and zoom in, I'm not getting my surface looking like a flat plane. There's some crinkles in it. There seems to be a very sharp turn that's happening at the origin. So no matter how far I zoom in, I'm not going to be able to get this looking like a plane. And that's what this definition of differentiability is trying to capture. That as you zoom in, zoom in, zoom in, it should look like a plane. If it doesn't, it's not differentiable there. This is unlike in calculus 1, where a function is differentiable if you can find its derivative. Here, we have two partial derivatives. And just because both of them exist doesn't mean the function's differentiable. A function's differentiable when it's approximated by its tangent plane. So that's the bottom line and the bottom difference there. And so what we'll do to finish off is we will just do the last couple examples next day, get into differential, and then we'll wrap up this section. So I'm going to stop the recording now.